So, uh, hello, welcome to today's live interactive session. In the previous session, we had solved some problems regarding reinforced soil walls. Right, we have solved some problems regarding the design of reinforced earth walls. So those problems were actually very simplified, just for academic understanding. Those were very simplified and those were taken from Corner's book. And so we had solved two problems in the previous class. And actually we were about to solve three. So one was left. So today we'll be solving that remaining problem. And then we will be solving some other problems on slopes. So, uh, so in the previous class, we had solved the problems. So first problem was with reinforced soil wall with the help of geotextile, right? So we use wraparound geotextiles to design our reinforced soil wall. And the second problem that we solved, that problem was reinforced soil wall using steel strips, right? So we solved two problems. One was using the geotextile and the other was using soil strips. Sorry, steel strips. Right. So the problem which we will be solving today is nothing but similar to the previous problems. That is our reinforced soil wall problem, but this time we will be using geogrid. Okay. Previously we used geotextile and our steel strips, and so sorry. And in today's problem, we will be using this geogrid. All right. So let us see the problem. So the problem says design a 7-meter high geogrid reinforced wall where the reinforcement spacing must be around 1 meter. Since the wall facing is of articulated precast concrete type of the same dimension. Okay. So we are to design a 7-meter high geo-reinforced wall. The reinforcement spacing is given as 1 meter. So why 1 meter spacing? 1 meter spacing because is precast concrete blocks that we are using. That concrete blocks, those are of 1 meter height. Okay, the dimension is 1 meter. So here this dimension of this precast concrete block is actually determining the spacing of our reinforcement. The coverage ratio is pointed. So coverage ratio is pointed means actually at each lift means at each lift means at each level. But geogrids do not cover the entire ground surface. Okay, so they are slightly separated. So we see like this. So this is the wall, and this is one lift. Okay, so one lift, two lift, three lift, like this. These geogrids are placed in layers. So in one lift, so there will be some. So the whole ground is actually not covered by this geogrid. So there are little gaps between these geogrid these layers that are good. So that's why we're using this coverage ratio. The length to height ratio of the reinforced soil should not be around 0.7. So one condition is given, um, which says that the length to height ratio of the reinforced soil should not be less than 0.7. Right? And the additional details are given in the diagram below. So if we see in the diagram, you can see we have a surcharge at the top. Right, 15 kilonewton per meter square surcharge is present at the top, and the strength, the soil properties of the reinforced soil are given. So phi r dash is 32 degrees, and we have gamma r, that is the unit weight of the reinforced soil. It is 18 kilonewton per meter cube. Then we have, for the backfill soil, we have the phi is 30 degree, the gamma is 17 kilonewton per meter cube, and then also we have the properties of the geogrid. So you can see the ultimate tensile strength of the geogrid is 160 kilonewton per meter cube. Sorry, per meter, 160 kilonewton per meter. And over that, we are using a cumulative reduction factor of 4. Okay, so there are many reduction factors that we use, right? So reduction for chemical biological damage, reduction for creep, then reduction for distillation damage, and similar other reductions. So all those reduction combined, the reduction is 4. Okay, the cumulative reduction factor is 4. So 160 divided by 4 will give us the reliable. Reliable is nothing but ultimate by the cumulative reduction. Okay, so 160 divided by 4. Yeah. Right. Then we have the factor of safety. Over that, we are again using factor of safety to get the design tensile strength. Okay. Design tensile strength of the required tensile strength. TLI simplification 40 divided by 1/4 times six. And also we have some other coefficient, that is CI, that is CI is actually called the interaction coefficient. Okay. It defines, it actually controls how the uh, geogrid actually interacts with the soil. There is some interaction coefficient we are using. That interaction coefficient is equal to 0.7. So all this coverage ratio, this coverage ratio is different. This interaction coefficient is actually determined from experimental results. All right. Also, two more things are given. So one thing, one we can see here is delta. Delta is equal to 25 degrees. So this delta is equal to 25 degree. This delta is actually the friction angle between between this block and this foundation soil. Okay, so that is delta. And then we have the bearing capacity of the foundation soil, that is given as 600 Newton per meter. All right. So these are all the given data, and we have to determine we have to actually design this. All right. So let us. The first thing that we will be doing is that here, the first thing that we will be doing, that is, we will be calculating the external stability. All right. So we will be calculating the external stability. So when external stability, what are the things that we have to do? The first thing is the sliding check, then overturning, and the bearing capacity check. So all these three things we have to do: the sliding, the overturning, and the bearing capacity. Right. So for the sliding and the overturning, first thing that we will determine is the earth pressures. Right. So the earth pressure of this. So we have the backfill soil here. So the backfill soil will be giving some pressure, okay, lateral pressure on the reinforced soil mass. So this is the reinforced soil mass, and here we have the backfill soil. So this backfill soil will be actually giving some lateral pressure on the reinforced soil mass, right? First, to determine that, first let us determine the earth pressure coefficient. So KB is equal to, so this is 30. So we have, right. So we have the earth pressure coefficient, active earth pressure coefficient for the backfill soil. Okay. Now the next thing is to determine the lateral thrust. Okay. So first we will be determining the lateral thrust will be coming from two things. One is this weight of the soil, and then the other thing is this surcharge. Is that it? So from the weight of the soil, we will be getting gamma B is gamma B 70. H is the height. So let us calculate this. So now the other earth pressure that is acting is due to this Q, right? Is nothing but Q to K height. What is Q? Is 15. So 15 0.33%. Right? Right. So total force 137.5 plus 8. Right. So 34.65 plus 137. But one is right. So this much is the lateral thrust that is acting on this reinforced soil. Right. I have to draw the reinforced soil block. It's is acting Q. Okay. These forces will be acting on this soil block, reinforced soil block, and this sliding force will be resisted by the frictional resistance that is developed between the interface of this reinforced soil block and the foundation soil. Right. The interface, there will be some frictional resistance that should actually resist the sliding of the input soil. Alright. So Now is calculate this sliding stability. So what is this resisting force F? It's nothing but W into mu. So what is W? W is nothing but the weight of this reinforced soil. All right. W is the weight of the reinforced soil block. So the weight times the mu. Mu is the what is mu? Mu is the coefficient of friction. All right. So weight times the coefficient of friction will give us the frictional resistance F. Now what is the weight? Weight is gamma R into H into L. All right. What is L? L is this weight. Length. This is L. Gamma R is the unit weight of the reinforced soil mass. So gamma R to H to L will give us the friction, this weight. W. This times the frictional coefficient is nothing but 10 delta, and this delta is known to us. Now, what is this L? So in the question, it is given that length to height ratio of the reinforced soil wall should not be less than 0.7. So let us take it as 0.7. So length to height ratio is 0.7. So what is length? 0.7 into 7. So it comes out as 4 meters. Okay. So what is gamma R? 18. So 18 into H. It is 10 delta. How much is delta? Is 20. Let's calculate this. 18 minutes. Approximately 20. So everything is in per meter length of the wall, right? So the plane strain problem. So per meter length of the wall, we're calculating everything. All right. Okay. Now, so what will be the factor of safety? Sliding, resisting force. Resisting force is the step divided by the disturbing force. So what is the how much is the disturbing force? 172.1. It's 1.67. This is greater than 1.5. So acceptable. All right. So sliding stability is done. What comes next? Next is the overturning stability. Right? This is the overturning stability. So generally, this overturning stability is not a problem for such reinforced arch walls, okay, or mechanically stabilized arch walls. Generally, overturning stability is not a problem because it actually cannot. It does not have this uh, inherent flexibility to mobilize the bending. All right. So due to that, overturning is generally not a problem. Always this overturning stability is generally satisfied. So let us just check that once. So what is this stabilizing moment? MS is nothing but stabilizing force times the U1, right? So what is the stabilizing force here? If you see this, what is the stabilizing force? P's are the overturning force, right? The force that will be stabilizing is nothing but the weight. Okay, the weight will be uh, what that will be actually stabilizing this, right? So 617.4 times the this L by 2. W is the stabilizing force. What is W? 617.4. Right. This is kilometer meters. Kilometer meter per meter. Now, what is the overturning moment? The overturning moment is due to these forces P1 and P2. So P1 times this height h by 3, P2 times h by 2. Okay. By 3. These are, as I mentioned in the previous class also, these are very simplified problems, right? So these are very, very simplified. These problems actually uh, do not consider the seismic forces and all other forces, right? These are very simple, just normal self weight and all this surcharge and everything. But this we are considering that, and we are not considering, we are not doing seismic calculations. All right. But in the exam or while we design, generally while we design in field, it's a little bit more complicated. There are a large number of forces that we have to consider. Also, we have to follow the total provisions and whatever it's mentioned in the book. Okay, I will mention in the book. We have to follow that, right? And as I said in the exam, if it's mentioned, always do the seismic calculations in whatever way that has been discussed in the class, right? Whatever way everything is being solved in the class by Professor Rajagopal. So follow those that procedure. Okay, because that is more detailed. He has considered this is like he has solved some examples in the class, right? Those examples contain this solution with seismic forces and all. So you can solve even you can solve these problems also by considering seismic forces by yourself. Right, and you can deal with this problem. Okay. So we got this stabilizing moment. Then now we have to find out the overturning. Overturning force into the volume. So P1 into 7 by 3 plus 2. How much is P1? 137.45. 6, right? Let's see how much does it come. 7 by 3 plus 30.6. 7 by 442 at once. Okay. Factor of safety 15 it's greater than 2, so accept. All right. Now, lastly, so sliding check is done, overturning check is done. Next is our this bearing capacity check. Okay. So first, let us find out this. Okay. So first, let us find this eccentricity. What is the eccentricity? By the vertical load. Okay. The moment divided by the vertical. What is the overturning moment? 442 divided by W. So W we already determined back 617.4 plus Q 15 into 5 is 442 divided by 617.4 into 0.6. Okay. This is less than L by 6 or D by 6 width of the base. Right? So, okay. So we have to check this. I told this in the previous class also. We need to check this criteria because we need to ensure that there is no tension at the base of the base reinforced block or the base of the footing. All right. So we need to check this. Now, what is the acting length, Meyerhoff's length, effective length or effective width? Minus 2 I6. 4.9 minus 4. Say so this say this is the import cell block. Okay, this was the import cell block. This is L. Right. So this is L. So it will have some the centers. This will have some centricity. So the effective weight will actually get reduced from L to LE. Okay, so what is the bearing pressure? In 18 into 7 is nothing but this weight. Okay, weight of this reinforcer. To 7 plus 18 is a surcharge 141 into 4.9. 4.9 is nothing but the width times 6.2. 3.62. 191 approximately. Okay, 191 kPa. Therefore, factor of safety is 600. This was given. By 121. 600 is the carrying capacity. This is given, right? It's given in the question here. 600 divided by 191. Yeah. It's greater than 2. So, again, acceptable. All right. So, external stability checks are complete. We did sliding check, overturning check, and then this bearing pressure. Done. Next, have the internal. Okay. So for the internal stability, let us write the expression for the horizontal pressure. Let's just we please recall how we solved this in the previous class. So same, similar to, all right. So let us write the equation for the horizontal pressure. So horizontal pressure is equal to horizontal pressure due to soil plus horizontal pressure due to this Q surcharge, right? So gamma into Z to KAR plus gamma into Z. Sorry, Q into KAR. What is KAR? KAR is 10 square 45 minus 5R by 2. It's 5 of the reinforced one. Okay. 10 square 45 minus what is 5R? Much was 5R? Where was 32? So yes. All right. Therefore, one is equal to 18 into Z to 0.31 plus 15 into 0.31. Therefore, gamma H is 18 into 0.31 is how much? 5.58. Z plus 15 into 0.31 is how much? 4.65. 0.6. So this is how our horizontal pressure is varying with this depth Z. All right. Now for vertical spacing, if you remember, sorry, just have to add some more pages. Now, if we remember our this what to say this design the spacing. So actually uh, our spacing actually ensures that the pressure, okay, so the load that is coming on the reinforcement is less than the design strength, design tensile strength of the reinforcement, right? Our the spacing of the spacing should be such that the oncoming load on the reinforcement should be less than the tensile strength, design tensile strength of that reinforcement, right? So using that design is been to by CR. CR is nothing but our coverage. Okay, so what was this design? We calculated in the first page, but 28.6 times SB into what is sigma h? This 5.58 Z plus 0.65, and this coverage ratio is actually given as 0.8. Therefore, we can get the spacing from here as 22.9. And if we Z plus 6. Okay, so this is the spacing. All right, so now what we can do, we can do some trial and error and then decide our spacing. All right. So let us check for maximum depth. So maximum depth was for maximum depth that was how much? Height. What is the height? 7 meters, right? Okay, it's just to check. So here, wait, here, if you remember our question, if you remember the question, what was the question? The question was given there. The spacing is actually what? Fixed as 1 meter. Right, the spacing is fixed. So how, why is the spacing fixed? The spacing is fixed because they are saying that this precast concrete blocks that we're using, the dimension of the blocks is 1 meter. Correct. Due to that, the spacing is also restricted to 1 meter. Correct. So this is what is given. The question. Correct. Now let us check for SV is equal to 1 meter. How much is the maximum this depth? Okay, how much is the maximum depth? So, if SV is 1, so 1 is equal to 22.9. 0.58. So please solve. If we solve this, say it is equal to 3.27 meters. Okay, 3.27 meters. So if we use 1 meter spacing, then the maximum Z depth that we have can go is 3.27 meter. So what we have to do is somehow we have to reduce the spacing. Okay, so initially it was given in the question that try for 1 meter spacing. Okay, but we saw that for 1 meter spacing it's not possible. For some depth that we have to, we can cover, it is limited to 3.27 meters. Right. So now what we have to do, is that we have to reduce the space. So now let us check for 0.5 meter spacing. Okay. So for SP equal to 0.5 meter, right? So if we solve this, we will get Z as 7.37 meter. Okay, that is fine. Our height is 7 meter, so it is fine. So what we can do is that so height of each spacing block is 1 meter, right? So the top three blocks, we can put 1 meter spacing. All right, so top three blocks we can put 1 meter spacing, and the remaining 4 blocks at the bottom we can put 0.5 spacing. So that will solve our problem. Right, so that will solve our problem. So let us just draw a rough figure how it would look actually. One, two, 3, 4, 5, 6, 6. 7. Okay, so 7 blocks. 1, 2, 3, 4, 5, 6, 7. Right, 7 blocks. How much? This is each block is 1 meter. All right, and we saw that top up to here we can provide 1 meter space. All right. So what we can do is that this is the ground level. So here we are putting 1 meter space. All right. And below 11. Pardon me for the background. Cross straight lines, huh? After that, we have eclipses with 0.5 meter. So if we count the total 11, right? So 11, 10, 1. All right. So these are the 11 geogrid layers that we can place. The top 3 that can be 1 meter spaced, and the bottom we are providing 0.5 meter. 0.5 meter spacing. And one more thing that is done is that to prevent this tension is eccentricity on each block, small geogrid layers are actually put like this. Okay. Small geogrid, this reinforcement layers are attached here. Okay, so that this there is no tension eccentricity on the facing block. Else what will happen? See, this is the facing block. We are putting the reinforcement here, right? So there might be some tension eccentricity. Okay, due to this pulling this facing block can get displaced. Just to prevent that condition, what we do is that we provide some small reinforcements here also. All right, just to prevent this eccentric loading on the, just to prevent the eccentric loading on the facing block. Else what will happen? See, like this, we have the facing block here. We are providing the reinforcement, right? So reinforcement will prevent that. So you can understand, right? We are due to this eccentric loading. So one reinforcement you are attaching here. So due to the eccentric loading, what this, so we'll get some eccentric loading, and this might get displaced, right? The facing block might get displaced. So what we do, we attach some small reinforcement layers at here also. Top and bottom both will have some reinforcement layers. So there will be less chance of eccentric loading will actually be distributed. The loading will get distributed, and there will be less chance of this displacement of the facing wheel. Okay, so hence this small pieces of small lengths of these geometries are also tied at the top of these planes facing force. Then now comes this total length, right? So this total length is nothing but what? Rankine length plus embedment length. This much is the LR, much is LE. Right? So how to get this LE? How to get LE? SV to FS pull out 2 into LE. C interaction. Okay, so sigma V spacing into horizontal pressure to factor of safety of pull out. That is the load, right? That is the load that is coming on the reinforcement. That load should be balanced by the resistance, shear resistance that develops here, right? Top and bottom of each this reinforcement line. Hence 2, right? 2 times LE, LE is this length, LE embedment length, LE times the interaction coefficient times this coverage ratio times the this load. Vertical load times tan delta, that will give you the horizontal load. Okay, vertical load times tan delta, that will give the horizontal load, horizontal pressure. So now let us write this again. SV, what is sigma h? Sigma h is this expression 5.58 Z plus 4.65. Fs pull out we can take is 1.5 times LE. Yeah, it's given as 0.75 times sigma V. What is sigma V? 18 into Z. Vertical pressure 18 is the unit weight times Z. Z is the depth times tan delta 1032 to CR. So we are taking this delta. Okay, we are taking this delta same as the friction angle of the soil. Why we are taking this? Because see, because we are using geogrids, right? So geogrid is like this net-like thing. The top also here we have soil, bottom of that also there is soil. So the interaction, there will be interaction between the soil to soil, right? Soil to soil through this big pores, big aperture of the geogrid, right? There will be soil to soil interaction through the aperture, through the this aperture, through this aperture of the geogrid, there will be soil to soil interaction. Hence, we will say this friction angle of the soil only here, 32. If we would have placed say geotextile, then we would have used the friction angle between the geotextile and the soil. Okay, if we would have used geotextile, then we would have used the friction angle between the geotextile and the soil. Why? Because there is interaction between the geotextile and the what? And the soil. But here, as we have big apertures, right? We have big apertures in this geogrid. There is interaction between the soil to soil interaction. Aperture, there will be interaction with soil to soil. Right? Soil to soil interaction through the apertures. So in place of delta, we are using this 32. All right. So from here, we can get LES 0.6 Z plus SLE. What is LR? H minus Z. This is LR. This is LR. Okay, now what we have to do, we again have to make this uh, table. Okay, similar to what we had done in the previous class. We have to make the table. So let us make the table. Use Excel for that again. Okay, I share the screen. Stop. Okay, so I hope it is visible. Please let me know if it's not visible. Okay, I hope the screen is visible. This Excel sheet. I hope the Excel sheet is visible. Right, please. If, if it's visible, please write in the text this message chat box. All right. Layer set the minimum power. This one layer we have 11. Then set 0.75. So 5, so 5, 5, 3. Right, so yes, we should give a bit of 0.75. And right, so what is LE? LE is 0.62. Just a second. So 0.62. 7. This we have LE. Now, what is LE minimum? Minimum we have to provide 1 meter, right? Minimum we have to provide n 1 meter. Now let us give it LR. LR is 3.88 minus 0.55 times much. Right. Well, calculated C. So all LEs are less than LE minimum, right? All LEs are less than LE minimum, so we will be using LE minimum only. So I'll calculate it with this plus all LEs are less than, right? So when we putting, so what we can do is that we can, it is up to you. All right, so you can put varied length also, we can put same length also throughout. So if you want to put same length throughout, you can put this 5 meter. Okay, and put 5 meter. All right, let's copy this. So we can register. Just a second, just share the screen again. So what is it? Just a second. Sit. Okay. So this is what we got. Okay, so this completes our design. So here we choose same length throughout. Okay, we choose same length throughout. Now, one more thing that we need to ensure is the connection strength. Right, we need to ensure the connection strength with the facing block and our this geogrid into at least. All right. So many researchers have given many things and we how to, and also we it was already discussed in the class how this testing is done, how the test for testing of this connection strength is done. Okay, so generally due to this conservative approach, So due to several uncertainties, this connection, T connection, the required strength of the this connection is actually taken as greater than equal to the design strength. Okay, should be this connection strength should be greater than 28.6 kilonewton per meter in our case. All right. This connection strength that we have to determine using the tests, using tests that we need to determine. This connection test that we determine has to be greater than or equal to this design strength. Okay, there is nothing but 28.6 kilonewton per meter in this case. All right. Now this was just the design, this stabilization design, right? So mechanically stabilized earthwork that design. Now, also in case of these walls, what we need to do is that we need to also take care of the draining. So in our case, we did not consider any water pressure or anything, right? In the calculation. So we're considering that the soil is dry. So what if it rains and the soil becomes wet? So in that case, we need to allow for proper drainage of water. So if we do not allow proper drainage of water, what will happen is that a huge amount of lateral thrust due to water will be acting on the wall. Okay. So to prevent that, what we do, we use some drainage. We provide some. So these are the face. Right? So we provide some drainage layer here. Okay. Maybe in front. This one in form of portionless sand or say gravel. Okay. We provide some drainage layer here. So this drainage layer is just some here. And also some specific criteria has to be maintained. Has to be maintained. Generally, one thing is that you need to provide some drainage layer here. Second thing is that if you are constructing, then you have to follow certain criteria for the backfill soil. So always our target should be that the backfill soil is also granular. Okay, questionless sand or say gravel. Okay, there should be a target that to provide a drainage layer and also to keep in mind that the backfill soil that we will be using or this soil that we will be reinforcing, this soil should be this backfill soil should be of uh, granular in nature. Okay, it should be granular in nature. So several researchers, several people have given several theories, theories or criteria for that. So you can follow any of the criteria and decide the gradation of the backfill soil. Okay, the size, particle size of the backfill soil. All right. So with this problem is over. So what we did, this was very simple, similar to the previous class. We solved initially what we did. So let us just see very let's see what we have done very fast. So what we did, we calculated the external stability first. We determined the destabilizing forces. Then we determined the sliding stability, which does determine the factor of safety in sliding. Then what we did, then we determined the factor of safety in overturning, right? Then we determined the factor of safety in bearing. After that, we can do the internal stability analysis. In that, the internal stability analysis, we checked and set the spacing, and also we determined the embedment length, right? Embedment length is the total length, right? And at the last, we commented on the connection strength that we should have, right? So with this, we completed our design. Okay, so this is complete, right? So this completes this reinforced wall, soil, earth wall design. Okay, simplified design. So as I will mention it again and again. So this is very simplified version. But when we design in field, we need to follow codes, oral provisions and also design it very carefully considering several number of forces. Right? Now let us go to the next topic. That is this embankment. Okay, embankment or slopes. So when do we call embankment and when we call it as wall? That is the question, right? So for any slope that is deeper than 75 degree, that is different. Yeah, that is actually designed as a retaining wall. Okay, so all principles related to geocentric reinforced soil retaining walls are used. And for slopes that are shallower than 70 degrees, generally you are designing it as embankments. Okay, so for the design of embankments, we need to keep in mind some things. Okay, generally slopes might be on weak foundations, right? Foundation soils over which the slope is formed and generally weak. In that case, this failure is actually what? Failure is actually of the foundations, right? And for steep soil of strong foundation soil, say the foundation soil is strong. In that case, we need to conduct this wedge analysis. So planar wedge analysis, slip circle analysis, but these are various wedge analysis that are conducted to determine to do the analysis, failure analysis of this slopes, steep slopes. All right. Now, during this analysis, which properties of the soil that should be used? So for the soils that undergo large deformation, that is soils that are based on soft formations, we generally use this constant volume or the critical state pressure value. Constant volume. So this friction angle, okay? Friction angle using this. So this is a derivative stress, the axial strain. So from this, whatever phi you are getting, that phi and c you are getting, that will return. Okay, and for soils that are strong, okay, for soils that are situated on strong foundation soils or soils that will slopes that will undergo less deformation, we use these peak values. Okay, use these peak values. All right. Now, as we can see here, for soils with phi is equal to 0. Okay, for completely cohesive soils, what we can do, we can take this failure wedge or trial wedges completely circular. And for C5 soils, what we have to do, we have to do this wedge analysis. We have to consider these wedges and then we have to solve. So for cohesive, completely purely cohesive soils, it's a little bit easier. And for C5 soil, what you have to do, you have to take these wedges and then so it's a bit complicated. So generally, all these things are generally done using these computer codes. These are not done by hand because it becomes a little complicated because it's practically it's not possible. Generally, it's not possible to do by hand. What we do use some computer programs or some software packages to which can select trial surfaces for us and then do the calculation. Okay. Okay. All right. So here just this factor of safety, how to determine this factor of safety is determined. So Cu into L times R is nothing but this mobilized cohesion. Cohesion times this length of the arc. Length of the arc is L into R divided by the destabilizing force. Destabilizing. What is the destabilizing force? So there is nothing but the moment due to this. Destabilizing moment is nothing but is the moment due to this weight of this mass, soil mass, right? And this is the planar wedge analysis where we consider a planar surface. Okay, we consider a planar surface, inclined at angle phi, and then we solve the problem. So let us solve this problem. Let us solve this problem. So let us read the question first. Assume you are dealing with a 10-meter high 50-degree angle embankment shown below. So I will show you the picture shown below, which consists of a silty clay. Okay, so the embankment is formed of a silty clay. The properties of the clay soil are given. Unit weight is 19 kilonewton per meter cube. The friction angle is 0 degrees. The C is 15 kPa. The area is 60 meters square. The center of gravity is also indicated. We will see that. This embankment is situated on a silty clay foundation. The properties of the foundation are also given. The unit weight is given. The phi is given. The C is given, and the area is given. Now, the first thing that we need to determine is the factor of safety with no geotextile reinforcement. Okay, determine the factor of safety with no geotextile reinforcement. Then determine the factor of safety with the geotextile reinforcement or allowable tensile strength of 40 kilonewton per meter placed along the surface between the foundation soil and the main soil. Only one layer of geotextile is placed at the interface of the foundation soil and the main soil. All right. And the third is determine the factor of safety with 10 layers of the same geotextile placed at 1 meter intervals from the foundation interface to the top of the organ. Assume that the sufficient anchorage behind the slip circle is available to mobilize the full geotextile strength. Discuss how the problem solutions would differ if granular soil were involved. Discuss how the problem solution would differ if granular soil. So this is this involved we have silty clay soil, completely clay soil. So we need to say that what changes, how do we need to solve if there would have been a C5 soil or 5 soil. Right? Now let us see this diagram. So you can see this. You can see this slope here, embankment here. So this is the embankment here, and here we have the foundation soil. Right, so here we have the foundation soil here, and here we have the embankment. All right, so all the properties are actually given. These angles are given, and this slip circle is also marked. Slip circle is marked, and also with the CGs that are given. CGs of the these CGs are actually this CG ABCD is this marks, and this is DFG and this marks. Okay, the CGs of this masses are also given. The properties of the embankment soil are given, the properties of the foundation soil. So what we need to determine is the first we need to determine the factor of safety when there is no geotextile placed. Okay, means unreinforced embankment. So let us see that. Okay, so first let us write down the weight of the wedge soil pieces. The weight of weight of A, B, E, D. So weight of this mass is nothing but unit weight. What is the unit weight? 19 times the area. Area of this APED is given 60 meters square. 60. 20 masses. All right. Then we have weight. What? 5 times what? 55 is the area times 80. Sorry, not 80, 20. 20, that's 20. Zero. Right? Now, what is this arc length? So this arc length we need to know because the frictional resistance, the resisting force, right? This resisting force will be mobilized along this arc length, right? Along this slip surface. So we need to know this arc length. So LAD is this. So how to find out? 2 into pi r by theta into 360. So 2y pi into r. So what is r? It's given 21. What is theta? 34. Calculate this. How much will it come? To that point. What is LDF? Same. Twice by 21. What is the angle now? 70. Point. Meters. All right. So we got the lengths. Now A. What was say factor of safety for when no reinforcement is there, isn't it? What is factor of safety? Summation of resisting moments. Summation of driving moments. Factor of safety CE into LED plus CF times this is the force. This is the force that will be mobilized. These times the radius that will give the moment, right? Cohesion times length will give the force times r will give us the moment times r. What is the driving moment? What are the driving moments? Weight. This weights. Where is the where will the weights be acting? These weights will be acting on the CGs, right? So weights time the distance of the CG from the point of rotation. Isn't it? So weight times is WABDE times is 12.5 and this weight times is 0. 0 because first the CG of this is actually coinciding this point rotation, center of rotation. Right? So it will be W 3 to 12.5 plus W G into 0. What is C? C is 15. Other C is 18. So 15 times 12 point how much? 46 we can 46 plus 18 times 25.65 by 1140 into 12.50 this into R. What is R? Sorry, 12.5. Which is R. How much is R? R is 21. So understood, right? So these are the forces that will be mobilized at each point. Each point. So force times this radius R that will give us the moment. Now let us calculate this. 0.96 is not acceptable. Okay. So without the reinforcement, this slope will fail. This slope cannot stand. This embankment cannot stand. Right? So without reinforcement, this embankment cannot stand. We need to provide some reinforcement. Now what is so what was the case first? What was the question for B? Determine the factor of safety with a single geotextile. Okay, so one geotextile is placed like this. Here, one layer of geotextile is placed. That case, let us see how much the factor of safety will increase. So, factor of safety is 13620. That will remain same. How much? What will be the additional T times Y? Y. What is T times I? Y. T is the mobilized strength. The strength of it. We are assuming that the complete strength of the geotextile or what a geotextile will be mobilized. So T is the design strength times the Y. What is Y? Y is how much will be Y? 17 meters from here to here distance. Okay. So we are placing the geotextile here. So from here to the point of rotation, it is 17 meters. So Y will be 17. So 40, it is given, T is given as 40 times 17. So let us see how much it is increasing. Very less. Very less. Just one. Okay, still not acceptable. Still not acceptable. Now what we can do? Let us provide more layers. Okay, more number of layers. So now what we are doing is that initially just one layer was placed, so now multiple layers we will. So now multiple layers we will. Okay. Summation TIYY. Summation TI. TI is 40 times YI. So initially is 70. So 1 meter spacing. At 1 meter spacing, so at this one meter spacing, we are providing this geotextile layer up to the top. So 70, then 60, 10 layers are providing. Then what? 15, 14, 13, 12, 11, 10, 9, 1, 2, 3, 4, 5, 6, 7, 10. The 10 layers are providing. Okay. So if we are providing 10 layers, let's see how much the vector safety increases. One 1.31. This is also not that much, so marginally acceptable. Okay, not that much. 131 is not. What we can do, we can increase the strength of the geotextile, but we need to ensure that the strength is mobilized. Actually. Right. So, or you can more number of layers. We can for 10 layers, we can say put 15 layers like this. We can increase the right. Now the other last question here was discuss how the problem solution would differ if granular soil. So, as I said, if granular soil, if granular soil would have been used, then we have to use the method of slices and wedges. So we need to take a slip circle, choose one slip circle, then need to divide it in slices. Then we need to do this process. Then we'll take a different slice like this. We need to do so. Generally, we need to make use of a computer program, a search algorithm, which can determine the this slip circle for us. Okay, slip circle for us and do the solution because manually it's a little bit lengthy and practically it's not possible. Also. We need to take help of computer programs. Right now, now with reference to the previous problem, determine how much embedment is required behind the potential slip surface in order to mobilize the allowable tensile strength of the geotextile. According to the transfer efficiency of the geotextile to the shear strength of the soil is 0.8 and the base the calculation of factor 51.5. Determine the total length of geotextile using Excel. Let us see one by one. Just a second. So it is asked determine how much embedment is required beneath. So say okay. Say this is question. It is asked like this you are placing. Like this you are placing the geotextile. Right. So it is asked how much this length, this embedment length, how much it should be there. Required behind the potential slip surface circle in order to mobilize the allowable tensile strength of the geotextile. Assume that the transfer efficiency of the geotextile is just pointed out. Okay. So for that, what we need to do is that so here, so generally I will okay, let me just write that first. So transfer twice E twice tau ELE is equal to TLR into factor of safety. So this is what? This is the strength, right? And here we have twice tau because top and bottom. Tau is the shear strength that is mobilized at the top and bottom. Okay, E is the transfer efficiency and L is this length. So here what we are assuming is that generally what happens as the embedment length increases. Okay, embedment length. So here we are considering that along this complete length LE, this tau is equally mobilized, isn't it? Along the complete length LE, we are considering that this tau or the shear strength is completely mobilized, equally mobilized along this complete length L. But in reality, what happens as this length increases, with increase in length, this mobilization also mobilization actually reduces. This concentration actually reduces with increase in this embedment. Okay, so but what we are doing for our case, we are considering that the shear strength will be linearly mobilized along this embedment line. And in that case, we are also, and one more thing, that one more factor that we are using is this transfer efficiency. This how much of this mobilized tau will actually be transferred to this reinforcement. That is given by this transfer efficiency, that is 0.8. Okay, how much of this mobilized tau will actually be transferred to the reinforcement? Okay, that is actually decided by this transfer efficiencies. All right. So now to calculate is 2. So what will be tau? So how much will be tau? Tau will be nothing but the shear strength. So shear strength is what? Shear strength here. Here, what will be contributing? So shear strength is or generally C right? Shear here shear strength is contributed by what? The cohesion only. So what is the cohesion? 15. What is the cohesion? 15. Right. So 15 2 into 15 times E times LE. What is T allowable? It is given 40. In the question only it's given to 1.5. All right. From here we can get LES. Let's calculate. To 1.5 divided by 2. All right. 2.5 meter is LE. Now it is said that determine the total length using the maximum distance from the slope face. That is slope face is this much, right? This is the slope face. So maximum distance from the slope face to the this failure to the failure plane is 8 meters. So total length 8 plus 2.5. Okay, 10.5 meter. Now, generally, what happens for commercially available geotextiles, the width actually ranges from around 3 to 4.5. Okay, to 3 to 4.5 meter. In that case, what we can do? In that case, what we can do? So one option is always that we are placing it like this. Okay, perpendicular. Okay, the length will be like this. Smaller direction will be like this. So in that case, obviously, we need to provide some seam or overlap along this direction, along the out of plane direction. Along the out of plane direction, we need to provide some seam or whatever. Okay, and we can also place in the other direction. If you want to utilize the strength of the other direction, we can also place it in the other direction. All right, in the other direction. In other direction, if you place, the seams will have to be given in this fashion. Okay, so it is up to the designer to which strength you want to choose, which direction strength you want to choose, how you want to place. All it depends upon the designer, and also whatever this calculation, whatever these values are, whatever values or whatever sizes of this reinforcement or geotextile, whatever is available in the market. So designer actually decides how to place a jacket cell based on all these things. All right. Okay. So this was just a very simple problem. Okay. Now let us see the next one. For a failed slope of known centroid and radius, resulting in a resisting moment of 2010 kN per meter and a driving moment of 2570 kN per meter, determine the factor of safety without reinforcement. Okay, no reinforcement. Then the number of layers of specified geographic ultimate tensile strength of 78.7 kN per meter, combined reduction factors of discharge. Okay. The average center of the reinforcement is okay. Okay. First case, what we need to do, we need to determine the factor of safety when there is no reinforcement. The second case, the required factor of safety is given. Okay. The required factor of safety is given as 1.4. The required factor of safety of 1.4 is given. And now you need to determine the number of layers that you need to put. Okay, the number of layers that you need to employ so that you get a factor of safety of 1.4. That is the target. So the first part, you need to determine the factor of safety when there is no reinforcement. And the second part, we need to determine the number of layers. Okay, the number of layers of yogurt that you need to put so that you get a factor of safety of 1.4. All right, let us see how to do that. First is factor of safety for unreinforced, right? Factor of safety for unreinforced. Factor of safety stabilizing moment by disturbing moment. How much is the stabilizing moment? 010. How much is disturbing moment? This will come out as how much? 0.78. So this, what does it indicate? This indicates failure, right? The stabilizing moment is lesser than the disturbing. So obviously the slope is going to fail, isn't it? So what we need to do? We need to reinforce the slope. Now we need to reinforce the slope, and what we need to ensure that after reinforcement, the factor of safety changes to 1.4. Right? The factor of safety changes to 1.4. For that reason, we need to determine the number of layers of reinforcement that we need to put so that our factor of safety changes to 1.4. Now, see, strength. What is the strength of the ultimate strength is 78.7. The reduction factor, combined reduction factor is 11.8. So let us determine the allowable strength. The ultimate by combined reduction factor. So this is 78.7 by 8. Much. 6.67. 6.67. All right. Now, what is the factor of safety? MS plus PIYI IMD. So this we can write as N. So same N number of layers T allowable into Y average. Centroid average it is given, right? The average centroid of reinforcement is. D. So how much is MS? 60 allowable, 6.67 B. Right. So implies 1.4 is equal to 2010 into. Okay. So 70. Right. So what we gonna so we use 17 layers. So we need to use 17 layers of this geogrid. So is to get a factor of safety of 1.4. All right. Okay, now here in this problem, we actually did not go into the detail of the design, right? How to uh, how to decide the spacing and how to decide the length, all right? Length of the reinforcements, all these things we did not discuss actually, right? So various researchers are actually given various methods and design charts using which we can actually solve this problem. We can actually determine the spacing, we can determine the length of the reinforcement, all these things we can determine using various design charts and various methods that are given by several researchers. Okay, so to name a few, Jewel et al., Ruger and Schmertman et al. So these researchers are actually given some specific design charts, okay, design charts using which actually we can determine the length of the reinforcement and the spacing of the reinforcement. All right. So Jewel et al. And Ruger, they actually considered that constant length of they decided that the constant length of reinforcement is to be placed along complete height of the slope. Okay, constant length of the reinforcement placed parallel to the slope face. Okay, whereas the other researcher called Schmartman et al. Actually gave method and charts where he gave lengths that reduce with that. Okay, so similar to what we saw in case of our reinforce this walls. Reinforce gave varying, okay, varying length. The length he varied the length of the reinforcement with the height of the slope. All right. Okay. So generally, the Schwartzman methods. So generally, Schwartzman's method is used for high slopes. Okay, very high slopes of very huge height. Okay, very high slopes. For very high slopes, this Schwarzman method is followed, and it is seen that for very high slopes, this failure surface is actually a logarithmic spiral. Okay, in that case, varied lengths with height that is employed, smart plane method is employed. But for slopes with low height or low to medium height, for slopes with low to medium height, it is seen that Jewell's method actually gives a more conservative. Okay, for slopes with medium to low height, this Jewell's method which actually gives us a result that is more conservative. Okay, let us solve one problem using this Jewell's method, right? Let's see the question. The question is, we plan to construct a soil embankment at a 70-degree slope angle with a horizontal and 10-meter height. Okay, plan to construct a soil embankment at a 70-degree soil slope angle with a horizontal and 10-meter height. To be reinforced with unidirectional geoplates having an ultimate tensile strength of 180 kilonewton per meter and combined reduction level of 1.1. The factor of safety is to be 1.4. The required factor of safety that we need to ensure is 1.4. The soil is granular with unit weight 18 kilonewton per meter cube. Pi is 30-degree and has no pore water pressure. Okay, there's no pore water pressure. This RDU is equal to 0. So RU is nothing but 1 pore water pressure divided by gamma into Z1. Say you have like this, say you have a slope. Like this, say you have a slope. Like this, say you have a slope chart. Yes. Now at any depth say Z, Z1, we have RU1. At any depth say Z2, there will be pore water pressures that are acting. Okay, along all direction. U1, U2. So this nothing but gamma into Z. So this ratio is called this RU. Okay. So we are considering that it is no pore water pressure. So no pore water pressures are generated. Hence, this RU will U is 0. So RU we are considering as 0. All right. Determine the number, spacing, and length of the individual geometry. So let us see how to deal with this. So to solve this problem, what we will be doing is that we will be using this Jewell's. Okay, we'll be using Jewell's. So you can see he has given many charts, and this is what? This is one of those charts. So here you can see this chart is for RD is equal to 0. Okay. Here we have these 3 parts. This chart. Okay. Here we have 3 parts in this chart. The first chart gives the minimum required force. Okay, this first chart actually helps us in determination of the minimum required force. All right, the minimum required force that will be acting on the reinforcement. Okay, that is given by this A requirement. And the second chart gives the minimum length that is required for the overall stability. The overall stability for the minimum length that is required for the overall stability of the system. And this chart actually it gives us the minimum length at the base of the slope that is required to prevent direct sliding. So this let me show you here. So this minimum length LR here, this LR represents the minimum length of the reinforced length at the base. Okay, so we have like this, the slope is there, right? So we are reinforcing the slope like this. So this minimum length that you need to ensure so that there, there is no sliding. Okay, there is no sliding. So that's same just to satisfy the criteria of sliding. We need to ensure this chart is given. Right. So this is for the overall stability. This is for the sliding. This is for the minimum required force. So let us see. So first, what we will do, we will find out the allowable strength. The ultimate divided by the action factors. Ultimate is how much? 150. This will come out as then. So now from here we can implement design safety. Okay, so this that factor of safety is what the factor of safety of this strength. It's given factor of safety is for the strength. Then we got the design tensile strength. Now what we need to now to use the charts to determine the different things. Now for beta, so in our case, what is the beta? Beta is the slope angle. Slope angle is 70 degree. What is the phi? Phi is 30 degree, right? So now for beta is equal to 70 degree and phi is equal to 30. So this is the graph for phi is equal to 30 and this is 70, right? To this one, yeah. Okay, so this uh sorry, yeah, so this point. Okay, so this point. Okay, so this is approximately you can take it as 0.19. This is approximate value. Okay. So approximately what you can do, you can take for beta is equal to 73 and K required is 0.1. Similarly, what are the other things for same from here? LR by H from here. Is same. LR by H overall and LR by H is direct sliding DS. These two we can get. LR by H overall it's 0.1. Direct sliding. Okay, so now what we can do, we can calculate the spacing. As B is given by T design by K required. So this is given by GL. Okay. So what is T design? T design is 31.2. 31.2 K required we got from the graph. Gamma is given 18 and what is the maximum height? Maximum height is 10. So here from here you can get the spacing. Comes out as 10. All right. Close. So if we provide even spacing, then total number of layers that we can provide, maximum number of layers that we can provide if the spacing is even. If we provide even spacing of 0.91, the maximum number of layers we can provide is h by hv stand by 0.91 is equal to 11 layers. Okay, so 11 layers we can provide maximum at a even spacing of 0.91 meters. All right, so spacing we determined, number of layers we have determined. What is the last thing that we need to determine? What is the last thing that is remaining? That is the length. Okay, the length of reinforcement. Now, if LR by H overall is greater than LR by H direct sliding, then use LR by H overall constant length throughout. Okay, if LR by H overall is greater than LR by H, yes, direct sliding, then we have to use LR by H overall as constant length throughout the height. Okay, and what is the other case? If not, use LR by H, yes, throughout. Okay, if not, if LR by H overall is lesser than LR by H ds, then what we can do? We can use LR by H ds throughout, or what we can do? What is the option? Or what we can do? We can provide LR by H ds here and then taper it out and reach LR by H overall at the top. So bottom we can provide LR by H ds and top we can provide LR by H overall, and we can just taper it out. Okay, in tapered fashion, we can just keep on reducing the height, length of the leaf. That we can do if LR by H overall is less than LR by H ds. But in our case, LR by H overall is 0.51 is greater than 0.3, right? So what we will use? We will use LR by H as 0.51. That is LR is equal to 0.51 into 10 is equal to 5.1 meter throughout. Okay, we will use throughout. Throughout, you will use the same length as 5.1 meter. Okay, same. Each of these have same length. All right, each of these reinforcement have same length of 5.1 meter. All right, because our LR by H overall is actually greater than what? Actually greater than LR by H. LR by H, this DS. Now, if LR by H DS was greater, then here bottom we would have provided LR by H DS and we would have tapered it out, reaching up to LR by H overall at the top. Right, we would have tapered it out, or we would have provided constant LR by H DS. Okay, these two options. So remember this criteria. Okay, if you are using this jewels method. All right. Okay, so I hope this is clear. Good. Now what we can do? Now we can use if you see jewels method, it is jewels paper. So he has given various methods to actually check whether the upcoming load is actually being taken care by the reinforcement. Those back calculation, these cross checks you can do. to ensure that your design is complete. Okay, so now let me just draw this once final figure. Just draw it. Yeah. So slope. So we are using a constant length of how much? 5.1 meter. 11 reinforced. Yeah, 1, 2, 3. So like this, there is no space. So 11 number of reinforcement at 0.591 meter spacing here you see. Okay. Six. All right. So, and one more thing you can do is that you can provide if we are using facing blocks again like previous cases what we can do to to prevent eccentric loading but even small layers of this geogrid again say 1 meter length can provide the top edge. Okay, like this. Okay. So with this we end this design of embankments and slopes. Okay. In the next class we will see what we can solve. Okay, whatever is being solved in the class, we will try to solve those problems. All right. So we'll see. So actually, not much questions are available. We've seen the next chapter, whatever in the next week, whatever is being taught, not much questions are actually not available. The textbooks or like that we can solve. We can practice problems kind of things. So we'll see what we can do. All right. So I hope this was clear. And with this, we will end today's session. Let's see how did we solve this problem. So we use Jewel's method. So we're using Jewel's chart. We determined all these factors. All right. So first we determine the spacing using this K required across determined in Jewel's chart. K required we got. K required we determine the spacing. Now spacing we decided that we will be providing equal spacing. So from spacing we determined the number of layers. After that, what we did, determine this lengths, the overall lengths we checked, we determined the overall lengths and this direct sliding lengths. And based on these lengths, we choose the length of the reinforcement. And then finally we give the panel diagram. Okay, about reinforcement. All right. So with this, we will end today's session. All right. So thank you for attending. Have a good day.